Hello, I'm Anna Mackay, and this video is on the equations of tangents, and it's the first of two videos in the Applied Calculus series, following on from the Differential Calculus series. So here we're being asked to find the equation of the tangent. Up till now we've just been looking at slope for the most part. My advice to my students would be create a visual as often as you can. So that means seeing that function, that graph, and typing it into your graphics calculator. And we're interested at when x is equal to -2. So let's see what that looks like. I'm just going to switch across to my emulator here. I've typed in the function, which was, in case you needed a reminder, x cubed, take 5x, take 1. We've got a standard view window, and let's draw that. And we're interested in what happens at the point as x is equal to -2. So a tangent will be a line that touches the curve at that point. So trying to imagine what the slope would be like. Is it an uphill line or a downhill line? I'd say it's uphill, and therefore the slopes of uphill lines would have positive numbers. So when we sub in the point of x equal to -2, we're expecting a positive number. We'll come back to this later. Whoops, sinking across here. So to find the equation of the tangent, we need to differentiate. So finding f dashed of x is equal to 3x squared take 5. And we're interested in the point at x is equal to -2. So we sub that point in. Now for my class, you are allowed to use your calculators from this point on. And we'll get 3 times by 4 is equal to -5. You can just jump straight to the answer if you like, of 7. So that is our slope. It's also called the m value. And as we're expecting, that is a positive number. So we're going to go ahead and use the formula y equals mx plus c to find the equation of a straight line. So I'll just refresh our memories here. Y equals mx plus c, where m is the slope at a given point. Sorry, my iPad's a bit slow today, and we've already found m. So let's substitute that in. Y is equal to 7x plus c. Now, here's the key thing when we're working with applied calculus. When you need to find the equation of the line, of a tangent, you need a slope and a point. They're the two key things that you need to find the equation of any line. So we have a slope, but we need a point. And a point involves an x and a y coordinate. We have the x. How do we find the y coordinate? Well, we're going to substitute x equals -2 into the function. And that's another trick with using for calculus. When you have a point, it's likely that you're going to use it in two places. The function, f of x, and the derivative, f dashed of x. So if you're ever stuck, just try that. Substitute that point into both of those two functions and see where it takes you. So we need to sub x equals -2 into the function itself. So -2 all cubed take 5 times by -2 take 1. That's catching up. And we are left with, where are my notes here? We're left with 1. And so therefore the point is -2, 1. I quite like to write it as a coordinate so it's easy to refer to. So there's our point that we're going to substitute in. You might like to write that off to the side, that we're subbing this in. So where you see an x, you're putting in a -2, and where you see a y, you're putting in a 1. So we are left, and we're solving for c. So let's keep the c on the left-hand side of the equals because it'll just make solving a little bit quicker. So we're going to have c is equal to 1, add 14, so c is equal to 15. And as you know, c is the y-intercept of that line. So finishing off, the equation of the tangent is 7x plus 15. Now, this was part A. Let's see what part B of the question is. So we're asked to find the coordinates of the point or points where the tangent meets the curve again. So let's create a visual for ourselves. Back to our calculators. Hope you've got yours handy. We've now worked out the equation of the tangent, 7x plus 15. Let's add that in, 7x plus 15, graph them. Okay, so the point where they touch is x equals -2, we've found that. Are they going to intersect again? Looks like they will. So if you have a look up here, why not have a look at the answer now? We're going to have to solve it algebraically, but let's see where we're heading. So for these calculators, G-solve, the intersection, here we are, y1, y2, and the first point is x equals -2, y equals 1. That's the point that we've already found, so check, that confirms what we're after. Now if we arrow across to the right, it'll tell us any other points, and there is one, when x is 4 and y is 43. So let's see if we can prove that algebraically. 4 and 43. Okay. So algebraically, what do we have to do? We're finding when those two functions meet. So where the curve and the line meet. Algebraically, that's where they are equal. So we put those two functions equal to each other. So the first function was x cubed, take 5x, take 1. And we're finding when that is equal to the tangent, 7x plus 15. And now we're going to use our algebra skills to solve for x. So bringing all of the terms over to the left-hand side, oops, no, it'll be take 15 there, take 15 is equal to 0, collecting like terms. All these skills that you've been practicing for years in maths come in handy. Okay, now you might be thinking, oh, I could possibly factorize a quadratic, but a cubic, I'm not so sure. But let's remember what we're dealing with here. We already know that the tangent touches the curve at x equals -2. Just a refresher, back in the days when you were just solving quadratics, if you had a quadratic like this, and you had a point there, let's call it 4, say, what would the factor look like? What would the equation of that possibly look like? Well, the factor is a repeated root. So you would have learned that whenever we have a touch where the curve is touching the x-axis, that gives us a repeated root. So the same thing when the tangent is touching the curve, that the point of where it touches, that x equals -2, will be a repeated factor. So we actually already know this. So it was x is -2, so as a factor it's +2. So we're going to have one other factor here. And this is where some skills come into solving this. So waiting for my brackets to load up here. There we are. So let's have a look at this cubic here. How could we possibly get the cubic term, the x cubed? That could only come from an x squared term and a single x. So remembering that this is a squared factor, so that becomes x squared. You're essentially going to end up with an x squared times by x, and that's how you'd get x cubed. Remembering that's not part of the question we're dealing with. So that's correct for this part of the factor. Now look at the constant term. We have -16. Now, when you expand out brackets, most of the terms are going to have x's or combination of x's in them. X's, x squared, etc. The only way that you could get a constant term is by multiplying numbers, nothing with an x in it. And so the only other position that we could have a number in is next to the x here. So you have to ask yourself, well, when I multiply this number by this number, I'm going to end up with -16. But be careful, that's not 2, it's 2 squared. So when I multiply 2 squared by something, I'm left with -16. So that's 4 times by something gives me -16. As you can see, we're after -4. And so that's the number that goes in our second factor here. You can check that by multiplying it out if you like. So that's the technique when you need to do one of these questions. This is quite complicated for early on, but you'll use it a bit later. But we need to find the point where they meet again. So that is one point that we knew initially the x equals -2, and so this is our other point where x is equal to 4. But go back and read the question. It said find the coordinates of the point, not just the x value. So you therefore have to substitute that x value into the original function. Don't sub it into the tangent because, because that's not the point on the curve that we're after when x is equal to 4. No, hang on. So we're going to substitute this into the original function. So we are after, hang on a second, will that work? 28 plus 15, now hang on, we can, what am I talking about? We can substitute that point into either the curve or the tangent because that's where they're going to meet. So pick the easier one, which is the tangent, less to deal with. So we're left with y is equal to 7 times by 4, add 15. That's 28 plus 15, which gives us 43. And remember, that's what it was back when we did the graph. X is equal to 4 and 43. But it said find the coordinates, so it's always nice to finish the question off writing it as coordinates. Okay, so moving on, we have one more to do, if my iPad catches up. So we have the tangent to the curve of this function here, where a and b are constants, and the tangent is 2x plus y equals 6 at the point where x is equal to -1. And we have to find a and b. So what do we do? Well, when in doubt with calculus, differentiate. So we're going to take this function and differentiate. I'm going to switch to the f notation. So f dashed of x is equal to 2x plus a. So there's our derivative. Now, to find the equation of a line, we need a point and a slope. So this is our slope function. Now, here's the equation of the line. Could we possibly work out the slope from that line, the equation of that line? Yes, we can. Now, if you're comfortable with general form, you could just probably read that off, but I prefer the y equals mx plus c form. So when it's in this form, this is our m is -2. So that must mean if that is the equation of the tangent at that point, then that must be our slope. So that means that is the answer to this part here, when x is equal to 1. So if we first of all sub in f dashed of 1, we have 2 multiplied by 1 plus a is equal to the slope, -2. So we can see here that we're going to get a is equal to -2, take 2, a is equal to -4. So we've got half of what we want. B, well, that's back in the function. So let's sub this value in to our original function. X squared, this time take 4x plus b. So what to do from here? Often in calculus, you'll have a point, and you often use that point in the derivative and the original function. We haven't used it in the function yet, so let's put it in there and see what we get. But we're going to be short a y value if we do that. We will work out the x's, but we won't have a y. The tangent is on the curve at the particular point. So if we were to sub in x equals 1 there, perhaps, then we can solve for y. And that will be the same y on the curve itself. So we're subbing this in, equals y. Perhaps I've done that the wrong way around. And what have we got there? We've got -2 plus 6. So y is equal to 4. So we now have a point, 1, 4. Let's use that to substitute it into the function and solve for b. So we've got 1 squared, take 4 times by 1 plus b is equal to 4. Solving that, 1 take 4 plus b is 4, and b is equal to 7. So that's the question. We're asked to find a and b, and we've got -4 and 7. That's the end of this video. The next one is on equations of tangents, part 2 of 2. Thank you.